Hi, everyone. So welcome back to this discussion on substitution reactions of alkyl halides. So we're still discussing alkyl halides and specific to SN2 reactions. And what we've seen so far is that these SN2 reactions, they involve a backside attack by the nucleophile on the alpha carbon of the alkyl halide. And the halide is lost to give us the product. Okay, so that's what this reaction is. So to write it, generally we can say that, okay, there is a halogen, there's some nucleophile. The nucleophile does a backside attack away from or opposite to the halogen. The halogen leaves simultaneously and it gives us our product, where the nucleophile now substitutes for the halogen, and the halogen is connected to this alpha carbon, which is del positive, and the nucleophile is now connected to the alpha carbon. Okay, so we've seen previously how the structure of the substrate or the alkyl halide, the steric bulk influences the reactivity. In this video, what we're going to do is we're going to look at other factors that are important. So the first thing that we want to discuss is leaving group ability. Okay, leaving group ability. So a better leaving group results in a faster reaction. And what you have to realize is our leaving group is this halogen, and after the reaction, the leaving group ends up as a halide ion. Okay, so this is a halide ion. So better leaving group, okay, you could think about it, it would be a good or a better leaving group if it is more stable relatively. When we are comparing something, a more stable leaving group is going to be a better leaving group because once it leaves, it is a stable species. Okay, so that is what a better leaving group be. So of the halides, okay, because this is alkyl halides, okay, the leaving group ability is iodide is a much better leaving group than bromide, which is a better leaving group than chloride, and then we have fluoride. In fact, fluoride is a very poor leaving group when it comes to substitution reactions. Okay, so you're going to focus mostly on these three. Those are the alkyl halides you're going to see. Either it will be an alkyl iodide, bromide, or chloride. Now, if you think about it, why is iodide such a good leaving group compared to bromide or chloride? How do we understand this? Have we seen this trend before where iodide is better than bromide or chloride? And think about it, it's connected to stability. Why is iodide more stable, or this is the most stable among these, and this is the least stable? Why is that? Chapter 3, acids and bases. So it is the same concept as conjugate bases. Okay, this has a bigger size, so delocalizes the electron density. Okay, that's what it is. And in fact, to relate this to chapter 3, it turns out most stable conjugate bases are good leaving groups. Okay, so we can use the same sort of parameters that we used to evaluate the stability of conjugate bases to evaluate the leaving group ability. What would make a good leaving group? So what were some of the things? So we could talk about electronegativity, we could talk about size, resonance is a key important feature, you know, so those are the sort of things that we will use or you could use to understand why a leaving group is better than another leaving group. It is better if it is more stable once it leaves. Okay, so that's as far as the leaving groups are concerned. Iodides are pretty good. Okay, they are very good, strong leaving groups. So that's one of the factors that's here, the leaving group ability. The other variable in this reaction is the nucleophile. So we're talking about each of these. So we've talked about the substrate, the alkyl halide. We talked about the halogen. Now we're going to talk about nucleophilicity or the nucleophile itself. And nucleophilicity basically is the way to understand this. It is a measure of nucleophilic strength. Okay, it's a measure of nucleophilic strength, how strong of a nucleophile it is. If it is a strong nucleophile, then there should be some attributes that we are looking for. If it's a weak nucleophile, what are some things that would tell those apart? So again, based on what the textbook gives us, and like I think I discussed this in an earlier video also, but something very simple to look for is charge. Okay, because a nucleophile, this is an electron pair donor. So it must have an excess of electrons in it to be able to donate. If I don't have something, how would I donate that thing? Okay, so if a nucleophile has to donate electrons, it should have a plenty or an abundance of electrons in it. So when you compare nucleophiles like hydroxide, okay, or hydroxide versus water. Oxygen has a negative charge, has plenty of electrons compared to water, which is neutral. So it's not like, it has electrons, lone pairs, but it's not like overflowing with electrons. So this is going to be a stronger nucleophile. Okay, this is a stronger nucleophile. That means hydroxide is going to give us a much faster reaction here, okay, because it's a stronger nucleophile. Water, being a weaker nucleophile, is going to give us a weaker reaction. Now, we can expand this to others. So think about methoxide, and we often see this as sodium methoxide, or for that matter, what you have to realize is this can be any Na plus OR. Okay, versus methanol. How is hydroxide related to water? Hydroxide is the conjugate base of water, or water is the conjugate acid of hydroxide. Similarly, methanol is the conjugate acid of methoxide, and if we have a generalized NaOR, then the conjugate acid is going to be the alcohol. And in all of these cases, because the conjugate base has a negative charge on it, it is a much stronger base compared to its conjugate acid. So most conjugate bases are stronger bases compared to their acids. Okay, most conjugate bases are stronger nucleophiles, sorry, compared to their acids. Now, Also realize that we've seen these molecules as bases in chapter 3. And what that means is nucleophiles and bases, they're pretty much the same species, okay? That means if a molecule is a nucleophile, a strong nucleophile, then it is also a strong base. If it is a strong nucleophile, it is also a strong base, because we've used these things as strong bases before. Now we are using them as strong nucleophiles because they pretty much do the same thing. They give away electron density. They have an abundance of electrons. They give away electron density. Okay. Now, so that's another feature that you're going to look for. And there's section 7.4 in the textbook that goes over this, so please go through that section. So nucleophilicity is another thing that we will look for. Now, one last thing, which honestly is not even on the slide right now, but it is very important as far as SN2 reactions are concerned, is the solvent that is used for doing the reaction. So solvent is the reaction medium. When we do reactions in labs, we need something to do the reaction, and that's solvent. That is very important as far as substitution reactions are concerned. And for doing an SN2 reaction, polar aprotic solvents are favorable. Okay, these are favorable, these are useful, or these promote favorable, promote the reaction. Okay, so these facilitate the reaction. Polar aprotic solvents. What does that mean? I think you're familiar with the polar term. That just means something with dipoles in it. Aprotic means there's no proton in that molecule. So I'll give you some examples of polar protic solvents and some examples of polar aprotic solvent, like the most common ones that you're going to see. Okay, so polar aprotic, these lack a proton. Polar protic, these have a proton. So examples of polar protic, because we've already seen this, would be water. Very simple example of a polar protic solvent, because realize that we know dipoles already. This oxygen is del negative, this hydrogen is del positive. That means this is a polar molecule. This is a polar molecule. Plus, since that hydrogen is directly connected to this oxygen, that hydrogen can also serve as a proton. So it is polar protic. Any alcohol that you can think of, polar plus hydrogen on the oxygen, protic, polar protic. Any amines that you can imagine. If we use amines as solvents, okay, they're also polar, and then you have a hydrogen on that nitrogen, so it's a polar protic solvent. So any of these solvents, they're polar protic, but they're not good for doing SN2 reactions. For doing SN2 reactions, what we need are polar aprotic solvents. So they should not contain any protons in them. So, so they can have oxygen, nitrogen atoms like that, but they do not have hydrogens directly connected to them. So a good example of a solvent that you're familiar with is acetone. This is a good solvent for doing SN2 reactions. So this is polar, it has dipole in it, but there is no proton in that oxygen. Okay, so it will be a polar aprotic solvent. Another solvent, this is similar to acetone. This is dimethylbromide. methyl sulfoxide, abbreviated as DMSO. Again, there is a dipole, so it's polar, but there are no protons, so it is aprotic. So it's a polar aprotic solvent. Okay. I just want to give you one more example of a solvent that you might commonly encounter. This is dimethyl formamide. Okay, again, polar, there's more dipoles in it, but there is no proton on the oxygen or the nitrogen. So it's a polar aprotic solvent. This is abbreviated as DMF. You don't have to know the structures per se, I would say, or you don't have to know these full names, what's the complete name of the molecule, but I would say you need to recognize the abbreviations at least, and at least memorize one of them so that you can use them as you're doing your work, okay? But the most important thing is to be able to recognize them, that if you see a solvent written, you should be able to identify if it is polar protic or polar aprotic, okay? So at least that much of a connection you should be able to make. Now, why are polar aprotic solvents good for SN2 reaction? Okay, that's the next thing that we're going to look into. And to do that, we again need to actually look at the polar protic first. That's easy to understand, okay? What sort of an interaction happens with a polar protic solvent? So imagine a reaction like this, okay? Let's say we have sodium hydroxide reacting with an alkyl bromide in some solvent. Okay, and we will choose two different solvents. In this particular case, our reaction is going to give us that alcohol plus sodium bromide as the product. This will be our reaction. Hydroxide goes and attacks that carbon, bromine leaves, becomes bromide. So it is Na plus and Br minus. That's a reaction. Now let's assume that, so we are going to keep everything else constant here. And let's assume that one of the solvents that we use for this reaction is water. Okay, so if solvent is water for doing this reaction, sodium hydroxide would dissolve great in water. So what would happen if we put this reaction, or if we do this reaction in water as a solvent? Okay, now the solvent, what it has to do is, it's going to basically make everything soluble. It has to dissolve everything, and then it has to facilitate the reaction. So what would happen when we add our nucleophile into water? Sodium hydroxide is Na plus and OH minus. So we'll have Na plus and we have hydroxide minus. And if sodium hydroxide is in water, okay, the water should be able to interact with the sodium hydroxide. So how would water interact with the sodium ion? Water is OHH. So I think because the sodium ion is positive, what the water is going to do is, the water has put dipoles in it. So the oxygen has lone pairs. It is del negative. So what's going to do is, it's going to interact with the sodium, because that's the negative part of water molecule. And not just one water molecule, there will be other water molecules as well. They're going to interact with the sodium ions. So there will be several water molecules which are going to form sort of a shell around the sodium ion, and they will make this, they will stabilize the sodium ion, because the sodium ion is positively charged. The oxygens all have electrons on them, and they have del negative charges to them. So they will come and stabilize that sodium ion. What about the hydroxide ion? The hydroxide ion is negatively charged. How would it be stabilized? Again, water can stabilize it because I think I can draw it here. And notice how each water molecule has hydrogens. These hydrogens are del positive because the oxygen is del negative. The hydrogens are del positive. And hydroxide is negatively charged, so that means they can interact with the water molecule. Probably not like this, but I'm just trying to show you what sort of an interaction is possible. This is del negative, this is del positive, del positive. So it's going to interact with the water molecule. And there will be like other hydrogens from other water molecules that are going to be interacting with that hydroxide. So that means the solvent in this case, what it does is it forms sort of a shell around these ions to stabilize them. So now, if this hydroxide has to react with this carbon, because this reaction is happening in the solvent. So if the hydroxide has to attack this carbon, the alpha carbon, it is not by itself. It's not like a naked like hydroxide in the system. It is surrounded by all of this solvent. So when it goes to attack this carbon, it is carrying all of these water molecules along with that. So what that does is it would make this hydroxide feel bigger. So if this is what if a hydroxide is basically a tennis ball with all the water molecules around it that are forming this shell, now it's a soccer ball actually. And for it to go and do this backside attack, it's going to be difficult because we saw earlier that, when you have a carbon like that, imagine a tennis ball coming and attacking this carbon versus a soccer ball and trying to attack it. That soccer ball is going to be difficult for the soccer ball to come and make an attack. Whereas the tennis ball being smaller, it can go and attack it easily. Okay, so because of that, what happens is polar protic solvents, they are not good for doing SN2 reactions because they make this nucleophile feel bulky, like it feels bigger than its usual self. And so it is slow to attack and do the reaction. That slows down the whole reaction. What would happen if the solvent were not water, but if it were acetone? Okay, so we'll go from water to acetone. Now that we've seen water, what happens in water, let's go to an example for a polar aprotic solvent. Sorry. So we're going to assume that our solvent is acetone now. Okay, so again, sodium hydroxide, we're going to consider sodium hydroxide. It's there, sodium plus hydroxide. Maybe I should write it here. You have sodium plus hydroxide. So sodium is positively charged. If you think about acetone, recollect the structure of acetone, carbon-oxygen double bond. The oxygen has lone pairs to it. It is del negative. This carbon is del positive. And so the lone pair is going to interact. So again, the sodium would be stabilized by several acetone molecules like that. So these oxygens are all del negative. They're going to come and make that sodium feel stable. Okay, what about the hydroxide? Negatively charged. The positively charged portion in acetone is this carbon. That is what is positively charged. So that means an acetone molecule has to come, and this carbon is del positive. It's going to interact with that. And another acetone molecule should come. This carbon is del positive. It should interact with the hydroxide. and so forth. Okay, so it's going to do some interaction like this. Okay, but now what happens is, I don't have it here, but compare this to the case where, or maybe I can draw it here, compare it to the case where the water was stabilizing the hydroxide. It could be any interaction like this, but where the water was stabilizing the hydroxide. Notice how the hydroxide in this case is surrounded by hydrogen atoms. These are small atoms. There isn't like a lot of bulk around them. And they can basically approach that oxygen and stabilize it nicely. But when you come to acetone molecule, the del positive is this carbon. But that carbon has now two methyl groups around it. And they would basically bump into the methyl groups from the other acetone that's trying to come in and then stabilize the molecule. Now, again, this tries to form sort of a soccer ball kind of a thing, but this interaction is going to be really weak because the acetone cannot come close enough, or if one of them came close to the hydroxide, the others cannot really approach because of all the repulsion that they're going to face. So there's going to be like some sterics here, sterics here, sterics here, you know, sterics here, sterics throughout essentially. And so for that reason, the acetone cannot come close to the hydroxide to stabilize it. So the hydroxide doesn't feel very stable. So that means as it is approaching this carbon to do the attack, it is easy for the hydroxide to break off these bonds and go attack as a hydroxide itself, or maybe with fewer of those molecules around. So it can do a good attack there. And so that speeds up the reaction. Whereas here, because these atoms can come really close to the oxygen, they form very strong. In this particular case, it's a hydrogen bond actually. Okay, that's another thing that you might want to keep in mind, that it's actually a hydrogen bond that's been formed. And remember that hydrogen bonds are the strongest intermolecular forces that are formed. So that hydrogen bond would be difficult to break for the reaction to happen, whereas in this particular case, it is some sort of a dipole interacting with another charge, you know, so not as strong, and so it's easier to break. So the hydroxide can now do the attack easily, and if it can attack easily, then the reaction is going to go faster. So that explains why polar aprotic solvents promote this reaction. Okay, so those were some other factors beyond the substrate itself. So we looked at the leaving group, you know, what sort of leaving groups are useful. We talked about the nucleophile, what helps the nucleophile, and then we talked about the solvent. So these are all factors that actually influence the SN2 reaction. Okay, these are all things that we need to keep in mind about an SN2 reaction. So that kind of wraps up the discussion around SN2. In the next video, we will go to elimination reactions or other substitution reaction. There's another one, substitution reaction, which we'll talk about. Okay, thank you.